Welcome everybody to today's Tech Talk. And it's my pleasure to have Pi presenting. He studied electrical engineering in Kiel, then moved to Berlin to the Max Planck Institute for Molecular Genetics, where he got a nanopore sequencer to work and measured things there. And then he figured that measuring computers is much more fun than measuring genes, and joined us about a year ago, where he's now working at the Green HPC project in the applications department. And he's figuring out how we are using the computer and how we could make that more efficient. And one part of that was to set up the ClusterCockpit, which he's going to talk about, where we can actually see what's going on in the computer, and you can see how your jobs are running on the system. And he'll use that, or we will use that, to make jobs more efficient. Just a few technical notes. We'll do the talk first, questions later. The slides will be made available. We have the pad online for questions from the internet, and we can use the Zoom chat for any technical problems. And we will have a tech talk on GitLab and how to use that by Georgiana and Wilton in February. We'll send more information when we fix the date. And if you have any other topics you want to talk about on the Tech Talks, or if you have something where you would like to see a Tech Talk on a topic, please contact us, support@DKRZ, and we'll see what we can do. And with that, the floor is yours, Pi.
Great, thank you. Thank you for the introduction, and it's my pleasure to kick off the Tech Talk season of 2024. And I'm excited to basically present a project I've been working on for now a year since I joined DKRZ, which is setting up and contributing to the development of a platform called ClusterCockpit. And ClusterCockpit is meant as a service for you as users of Levante. So why would we want to talk about performance? I mean, for you, the reason is obvious. You're here, so you had an interest. But the reason to talk about performance of jobs is basically, if you improve the performance, you improve your throughput. And more throughput is more science per day. The bit less obvious reason to also talk about performance is energy efficiency. So the faster I can get my job through the machine, the usually more energy efficient I am. This is basically the background motivation why we also got funding for this project. So this is sponsored by a grant from the BMBF in the Green HPC call. Now, the only take-home message I have for you today is basically clustercockpit.dkz.de for you today. So if you bookmark this, I'm already happy. And today, through the talk, I basically want to guide you through this platform, tell you a bit what it is about. We have a bit talk about performance metrics, so how to read and interpret these values. And I will close the talk with giving you some use cases. So basically, what is it good for? Now, if you question monitoring at DKRZ, what we have so far is actually not that much. So what we once have is what you see here on the right side, this Grafana dashboard hosted on monitoring.dkz.de, which shows you a very high-level view of the utilization of the system, the current queue status, but it's far away from being job-specific. And apart from that, we have a couple of command line tools from the Slurm cluster manager, which is basically before the job as queue, where am I? When is my job supposed to start? During the job as control show, some information, where is it right now? And afterwards, yeah, I'm basically at log files, maybe as act, and that's it. So now if I'm interested in my job executed, it didn't fail, which is the first maybe milestone. But then what actually happened on the nodes I allocated and that computed my job? And until now, you're basically blind from this eye. And we would like to change this. So starting with the guided tour, if you log into ClusterCockpit and your normal user credentials should work as long as you are allowed to submit batch jobs. So that's the only condition. Then you will land on this page here, which is basically showing you a brief summary, how many jobs you are currently running on the system, how many you have run in the past. If you then click on the My Jobs tab, you get a first summary of what you submitted so far and what we've tracked. I will talk about that later, which is divided in these two areas. So on the top row, we have some meta information, how many jobs, how many node hours you've used so far. some histograms on how long your jobs run, how many nodes you use, basic statistics, or what you're doing on the system. And then in the bottom, you have a list of the past jobs, so most recent top in this case, which show you already a few more details. So for me, this is test account, so only one Jupyter instance I pushed on the compute node here. What you then see is already the job name, the job ID, on which node the job was executed. And then you see a couple of these graphs here on the right, and I will explain those in a few minutes. Now, if you click on one of these jobs, you get even more details about this one. So starting again in the top row, some meta information. Then you get a polar plot with a basic footprint, showing that for a more reasonable job in a second. You get a roofline diagram and then a bunch of metrics. So we started measuring basically everything we can on the node during job execution, and we are now providing these informations to you. Talking about job footprint, so this is a footprint from an icon job, which you already see. So how to read this polar plot. This is basically a couple of interesting metrics, which is stuff like CPU load, the memory usage, memory bandwidth, and each of these axes is scaled to the technical limits. So mem usage of 256 gigabytes would here be scaled to 1. Same for CPU load. In this case, we are scaling to the 256 threads, so using SMT. And same for memory bandwidth, InfiniBand, and so on and so forth. And you would rarely see that this full area here is covered, because this was basically mean a burning node, and that's usually not happening. So what you usually see here is you're either compute bound or mem bound, or you're mostly idle, in case, or in my case, where I push just a Jupyter, which is mostly doing nothing to a compute node. Then on the right side, you get these roofline plots, and for like deeper details on these plots, I would like to refer you to the literature in the interest of time. But basically, a basic readout of these is, if you're to the left side of this NIC here, your application is more in the area of being memory bound. So the limit is basically the data you can stream from the machine's main memory. And I can already tell you that this is the prominent use case at DKRZ. So for the second one, where you have an application which is compute bound, this means the numeric pipeline of the processor is the limiting factor. And I had to really scroll through a couple of jobs to actually find an application which is using the flop rate, so the double precision arithmetic of the CPU. And these dots are color-coded. Legend is missing because it's a project in development. So this is coming issues open. Now, below these plots, you find a bunch of these metric plots, and it needs not much, but a bit of training to read these, and also to get a valuable readout, which actually helps you in your work. So taking here the example of, this is a graph of a CPU load from a job. And what you basically see that after a very short init phase, the load is more or less static at 128, which means somebody spawned very likely 128 ranks of something doing stuff. That's not more, or you can't get much more out of this plot. So the dashed line is configured from us to something. So the config name is really normal. And now you're already asking what is normal. But we don't really know. So this is a reasonable value you might target for. So really carefully speaking. And for a CPU load, it's really reasonable to try to achieve to get a load of 128 on these nodes. And then the second information here is the level at which we measure this metric. And this is currently always node. So we are reporting all these metrics on node level. We are already measuring at higher resolution. So for instance, floating operations can be counted per core, which is for a larger job, really a large amount of information. That's why we are aggregating this and at the moment only displaying node level metrics. This will likely improve in the future. So we might go down to socket or memory controller level for memory. We might also display accelerator level for GPU metrics. So this is all basically in the pipeline right now. Now, if your job becomes a bit larger, these plots become quickly crowded. So after 50 nodes, the front end starts aggregating these values and is only displaying min, mean, max per metric, which looks like this here on the right side. And only if you open the job details, you will get all the measurements per node. And then their plots might sometimes be colored. And this is on two levels. So we have basically a caution and an alert level configured. Sometimes it means you're above a threshold, depending on which direction is actually the critical one. Sometimes it means you are below a threshold. So for instance, if Flop's plot gets colored, it usually means you're below a threshold because we want to utilize these nodes as much as possible. Same for CPU load. If you're below a certain threshold, you will get notified. And it's the opposite direction, for instance, for InfiniBand or Lustre metrics, where usually the opposite is true. So too much Lustre traffic, too much InfiniBand traffic is an indicator that this might harm your job or hinder it. All right, then a bit of technical backgrounds of what you might see and what might be a bit tricky, but which is not really an issue. So the first thing is that we have a constant measurement interval of 1 minute. So we are collecting all these metrics from all the nodes in Levante every minute, but Slurm is obviously not caring about that. So Slurm is scheduling jobs on the node as soon as the resources become available, which can lead to some artifacts like shown here on the left side, that you actually see a bit left over from the previous job on the node. So if the job starts at second 30, half of the measurement is from the previous job, half of the measurement is from your job, leading to some funny results sometimes, but just ignore these border values. The second thing is even deeper in measurement technology. So if you see a plot like this of a memory bandwidth, you could already tell there's something fishy with this job, so it's not ideal, but it's also not as bad as this plot might suggest. Because what happened in this case is what we call aliasing, and aliasing simply happens if my sampling frequency is too low. So if the underlying signal frequency becomes too high, then if I sample with too few samples, I get arbitrary wrong signals. And this is illustrated here at the bottom of the slide, where the black is basically the signal I want to measure. And in this extreme case, if I sample at the marked dots, like for instance, in this case, the measurement signal plotted in red has nothing to do with the underlying reality. With two exceptions, because if you look carefully at this bottom plot, what holds true, even though the measurement is completely wrong, is the minimum and maximum. And this is why I said that this job has some room for improvement. So if you have a memory bandwidth of around like 100 gigabytes per second, the node is capable of doing way more. So if you have these measurements, don't be scared. It's not that bad. It's just that the measurement is, or it's a technical limitation. We are working on this. So for instance, for node power, we are currently working on increasing the sampling frequency to 1 second and then aggregating or averaging these values on the node for each minute. And this should basically fix these artifacts. Now, having this platform set up, what is it good for? So why is it worth visiting this for you? And why do we think that even though this is a project in development and you will find bugs and breaking bugs and the platform is going to change over the next years, we still think that it's ready and that it's worth for you to visit. And I'm showing you why. Because it's intuitive. So in contrast to these command line tools where you have to really dig deep and know your job. You know your job, I know, but it's really hard to get the information you need. And with ClusterCockpit, we're trying to aggregate and collect this in an easy, accessible way. So I picked this one. Sometimes I'm just job browsing and stalking you. And I found this one. This is 101 nodes job. And you immediately see that this is not really utilizing the nodes. So the CPU load is dangling around at maybe 40. You have almost no floating point operations going on. Memory usage, I mean, every node has at least 256 gigabytes of memory. So using 30 is really on the lower end. And most importantly, our applications are usually mem-bound. So if you're not doing floating points operation and you're not running into memory or memory bandwidth capping, then this job needs optimization. I can't tell you at the moment what's the issue. It's just pointing you to this job is worth a closer look and worth some optimizations. Another one. With this one, I picked this one because from outside, and it might be wrong, and then this is just a false positive, but if this is a load compute checkpoint restart pattern, then the ratio of this rather long init phase here and an equally long compute phase is not ideal. So you're almost using half of the allocated compute time for init phase. And if this is true, that this is the job pattern, because I found many of these jobs for this user, then a simple and quick fix might be to increase this compute period. If this is disconnected experiments, I'm wrong. So then it's as it is. So still on the user side to basically decide if it's worth a fix, if it's just 10 of these experiments to finish revision, also good. So just from the observation perspective from us. And last but not least, one of my favorites, if your compute or your CPU load is hard capping at 32 on a CPU with 128 cores, this is a really good indication. If you then look into the job script and somebody configured omnum threads 4, if you then check the binary and the binary is not loading any OpenMP implementation, clear case of forget to compile with OpenMP. And for your excuse, hard chances until now to figure this out. So you would really need to figure out or check the log files, wonder about why the runtime is not as fast as expected. But with this new platform, this should be way easier to detect and to fix, obviously. Now, basically blaming a bit some of the cases where things are not ideal on the machine, the question arises where or what should you aim for? What are reasonable values for all these metrics displayed? And to answer this question, I sampled the data we have for the first week of this year, just to get an idea basically of what's going on Levante. I excluded the shortest jobs, so I picked only jobs running for more than 5 minutes that also exited with a exit code 0, so completed for 1 week, and only compute partition, so leaving out GPU and interactive for the moment. And then I basically plotted the distribution of each metric, so the average per job, and then the distribution across all these jobs. And it's, even though it's only a week in 2024, it's a bunch of jobs. And the distribution between number of jobs and consumed node hours is really interesting. So the short jobs are, in terms of numbers, the majority. It's 11,000 jobs in only 1 week. But in terms of node hours, the jobs with more than 10 nodes are the interesting ones. And if we talk about optimizations, we never talk about numbers of jobs. So that's not really the goal. The goal is what's consuming the most of the node hours on the system, both from in terms of throughput, but also in terms of energy perspective, energy consumption. This is the major focus. And then you will see plots like this here on the right. So here's one example for CPU load. So always these 3 columns for the 3 job categories, and then just box plots showing you the distribution of the average value for this kind of metric. Now, I tried to group these metrics a bit. So there's a set of metrics where it's usually a good idea to be on point. And one of these metrics is CPU load. So this is basically a configuration. You want to configure your job in a way that you have enough ranks to fully utilize these 128. Or in some cases, it might be reasonable to use the hyperthreading, or SMT as it's called, and go for 256 ranks on this node. And you already see a common pattern in our field that one node is basically falling off, which is either some overhead at the end or maybe an IO node. I can't tell for this particular example, but we do see this kind of behavior quite often. Now, if you look into the CPU load, you already see the issue. There's a ton of short jobs which underutilize single nodes. So it's these less than 5 node jobs, but it's not that much of an issue as it sounds like, because they are not using so many CPU hours. And then for these larger jobs, illustrated here in green, they usually, at least on this level, utilize the load. So same for memory bandwidth. Here, an example plot. Most of the nodes are at a constant level of 20 gigabytes, which is, I would say, the lower bound. So all nodes have 256 gigabytes. Some have even more. But if you look into the distributions, this plot here on the left side is a typical case. So same picture as above. The single node jobs are usually using less resources, while the larger setups might be a bit tuned a bit better, but still there's room for way bigger jobs from this perspective, obviously. Now, the second category I made is basically the metrics we measure where more is more. So really let it burn as much as possible, because this is what we are operating the system for, to actually do something reasonable or something meaningful. And this is the floating points operations if you're compute bound, or the memory bandwidth if you're memory bound. In the top, I'm showing one example, which is, I have to say, doing a decent amount of floating point operations, because if you check this dashed line here at 100 gigaflops, which I arbitrarily marked as normal, is even if you only consider scalar double precision operations possible on the system, way beyond the possibilities of the architecture. And if you also take into account the vectorized instructions, 2.5 teraflops is far out of reach for almost any job on our system. But that's perfectly fine, because as you then see on the second row, we often see, this is an example of an icon running on 8 nodes, we see jobs that come, I must say, surprisingly close to technical limits. So we sometimes see jobs that get almost to 300 gigabytes per second memory bandwidth. And the limit, so if you run Stream, which is really a benchmark, so you can't get higher, 360, that's impressive. And this is really well-tuned setups where the nodes are really on their limits. So this is great to see. But if you then check the statistics, it's few of them. So the majority is getting, and that's why I put the normal line here around 100. The majority of these setups is somewhere getting to these 100 gigabyte range for memory bandwidth. And last but not least, there's a group of metrics where basically to complete your job as much as needed, but they affect, first of all, your job, and in some cases also other people's jobs. And this is everything which is related to networking. So in the top row, you have the combination of how many file open calls you send to the Lustre, and in combination with that, the bandwidth used to the Lustre. And this, again, typical example, you have a lot of file opens in the beginning when all the binaries, config files, you name it, are loaded. And in this case, it looks like you have, after an initialization phase, you have a second peak here where another set of files is loaded. And then if you map this to the bandwidth, so basically the volume transferred from the Lustre, a ton of files in the beginning, but only with very little sizes. And then the second peak, maybe it's loading a checkpoint, I don't know. But this is visible here. And then second interesting observation, this is already aggregated, but since the green line is the maximum, it seems to be only one node is really seems to be responsible for this traffic. Maybe also a case interesting to look at. Statistics here kind of expected, I would say. So it's not really that you can find outliers from this far away. Then the last one here is InfiniBand, and since cluster is going over InfiniBand, you will always see an overlap between this metric. So if you have cluster bandwidth, you automatically have InfiniBand bandwidth, but during the compute phase of the job, it's more likely that then the InfiniBand bandwidth is actually caused by your MPI or whatever communication between these nodes. Here also very typical for our system that you have these bimodal distributions, which indicates some coupled setup where some nodes need way more communication, while others, like here the ones on the bottom, need less. And this is the communication plot. I just showed it for this case here, where you can again nicely see this init phase where basically the nodes work mostly independently, and then this compute phase here where you have the actual internode communication. Limit in this case 100 gigabits, so full duplex, so 12.5 gigabytes per second. If you see in the Lustre bandwidth, and for me have been playing with this, more than 12.5 gigabytes per second, don't be surprised, the Lustre has a cache on the client. So if you exceed these limits, it's not that you found new network connections, it's just a caching artifact. As I indicated at the beginning of the talk, this is still work in progress, and that's why we have a couple of limitations here. The first one I already told you about is we are at the moment only displaying node level metrics. This is just a handling reason to not explode our time series database. The second one is about importing jobs. So right now we are ignoring jobs shorter than 2 minutes because metric plots for like 2 samples are meaningless. So these fall under the table, and we are only importing in batches every 5 minutes. So if you start a job, it can take up to 5 minutes until it will really show up in the ClusterCockpit front end. And also for storage reasons, at the moment, ClusterCockpit is configured to forget all its data after 6 months. So you won't be able to see jobs older than that. And also important, the front end is showing you statistics about node hours of your user and of your project. These are computed out of the data inside ClusterCockpit. So the node hours of your for node hours of your project, the DKRZ loop is always the resource to go, and ClusterCockpit will only give you the statistics of the past 6 months. GPU partition, very interesting, but under development also from our side. So at the moment we have no way, or haven't found a way. I can't say if it doesn't exist, but we haven't found a way to really measure flops and memory bandwidth on these GPUs. We have some proxy metrics like the load of the execution core, whatever that means in NVIDIA speech. And we have the load of the memory controller, but both of these metrics are just percent values, so value between 0 and 100%, which is an indicator about if your job is doing anything on the GPU. But for instance, memory load utilization just means that at least 1 byte got transferred at that point in time. So it's not really scaling with the actual throughput. So this is one of our basic improvement targets at the moment. And GPU power is currently disabled, so we are not showing it because it's heavily affected by aliasing. So GPUs seem to be way more dynamic in their power consumption than the CPU nodes. And we are currently working on improving this, because one of the interesting questions would be, now that I've ported one of my setups to the GPU, could you please give me the energy consumption of this job, that I can only assess the speed up, which is easy, but also the memory or potential memory savings. So this is also one of our priority targets, to basically provide you with energy measurements per job to complete this. And last but not least, some things are simply hard-coded. So for these all kind of filtering methods within ClusterCockpit, some are just hard-coded at the moment to floating points in memory bandwidth, and for instance, do not allow to filter for InfiniBand traffic or some in-house specific metrics. Now, to basically sum this up, so the main goal of today was basically introduce ClusterCockpit as a new platform for your monitoring and basically your Levante software stack. I wanted to give you an overview, or ClusterCockpit is able to give you an overview of what's going on the system under your name and what happened in the past. I tried to introduce a bit how to read these performance metrics and what you can or what you could get out of these measurements. And I tried to give you an idea of how good are these how good are these limits currently utilized. So if you have a specific job that you can basically assess, this is or performing on average, or this is actually very well tuned, or this might benefit from some hands-on time. And not forgetting this one. So ClusterCockpit is not our own development, but this is all developed within this EHPC grant, together with the universities of Erlangen, the HLS in Stuttgart, the University of Aachen, and industry partner here is HP. And with this, I would like to close the talk. So first of all, thanks for coming and thanks for listening. And I'm happy to take any questions.